In this screencast, we're going to finish up some notes on energy, and then we're also going to take a look at some examples using energy bar charts and some websites for interactive simulations on motion. So in class, we did have time to look at a couple of definitions of energy and different forms of energy. So we saw that from the law of conservation of energy, you can never create or destroy energy, but you can transform it from one form to another. So we looked at some forms such as kinetic energy due to an object's motion, gravitational potential energy, elastic potential energy for things that are stretchy like springs or rubber bands, things like that, and chemical potential energy, or the way that energy can be dissipated, usually in friction, as thermal energy. So in one class we had time to go a little bit further, but in the other class we didn't. So just a reminder that kinetic energy depends on a couple of factors. It depends on the mass of the object and how fast the object is moving, its speed. And we're not going to actually have to use this equation at all, but if you have trouble remembering what factors affect kinetic energy, you can think about 1/2 mv squared, and you can see that the velocity plays a bigger role in that motion energy than the mass does because it's squared. If you're looking at gravitational potential energy, it depends on the mass, the acceleration due to gravity, which on the surface of the Earth will always be the same, of 9.8. And it also depends upon the height that that object is at. So an equation we can use is mass times g times h. When you're thinking about elastic potential energy, it depends on how far that object is either stretched or compressed. So there are some springs where if you stretch it, you can store energy in it. And there are other ones where maybe if you compress it, you're storing some energy in it. And it also depends on the stiffness of that object, how difficult it is to stretch or compress it. And then dissipated energy is typically going to be referred to as thermal energy. Depends on what kind of heat is produced. Alright, so on page 96 in your workbook, there's an example problem here where we have a roller coaster. I'm going to use this to help illustrate how we can use energy bar charts to represent conservation of energy. So if you look at this roller coaster at position A, we know that it has a certain amount of kinetic energy and a certain amount of gravitational potential energy at that position. So this line here indicates that it has 2,000 kilojoules of gravitational potential energy and it has 500 kilojoules of kinetic energy. So it's in motion even though it's at the top of that hill. If we wanted to plot that as a bar chart, you can see we have labeled here the gravitational potential energy and kinetic energy. We would make a bar chart so that it represents that the gravitational potential energy at that position is up at 2000 and the kinetic energy is at 500. So can draw those in. And then from conservation of energy, if we wanted to know the total energy here, we would just add up gravitational potential to kinetic. And so we'd have 2000 plus 500 is 2500 kilojoules. So if there's no energy dissipated into heat as thermal energy, at every single one of these positions, the total energy is going to have to add up to 2500 kilojoules. So in this next position, position B, we can see that it has lost a little bit of gravitational potential energy because it's not at such a high height. So it only has 1,000 kilojoules of gravitational potential energy. And then if we wanted to know how much kinetic energy it has gained as it goes down, we would have to take the total energy, which we decided was 2,500, and subtract 1,000, and we'd be left with 1,500 kilojoules of energy there. So if we plot that on position B, we'd have 1,000 of gravitational potential energy and 1,500 of kinetic. So kind of following that same procedure at C, it has 0 kilojoules of gravitational potential energy, so everything has to be kinetic, all 2,500 kilojoules. And at position D, it has 1,000 kilojoules of gravitational potential energy, so 2,500 minus 1,000 gives us 1,500 left in kinetic energy. So what you'll notice here is that from conservation of energy, the total energy that the roller coaster has to stay the same at every position. It has to add up to 2,500 kilojoules, but you could see that it could change form. So it decreased some potential energy as it was going down, while the kinetic energy went up. It means it started moving faster as it was going down this hill. Alright, so there's a couple more things for you to try and practice using these energy bar charts. So on page 97 there's another example of a person kind of jumping off of this platform. The notation used here is a little bit different. PE is used to mean potential energy or gravitational potential energy, and KE means kinetic energy. So just pause this for a moment and try this out on your own, and then check your answer. Alright, so hopefully you've had a chance to try this out on your own. At position A, we know that it has all gravitational potential energy of 15,000 joules. So kinetic energy would be 0, and that one would be up at 15,000. At the next position, we know that then the total energy has to be 15,000. So if there's 11,250 of potential energy, we have to take 15,000 minus 11,250 in order to get how much kinetic energy is left. And if you do that, you'll get 3750. So that's what those bar charts look like. At position C, until it's about halfway down, the potential energy is half of what it started with. So the remainder has to be kinetic energy, or 7,500. So those two bars should be up at 7,500 here. Alright, at position D, the potential energy has gone down a little bit more to 3750, so 15,000 minus 3750 is going to give us 11,250 for the kinetic energy. And then at position E, all of that potential energy the person started with has now been converted into kinetic energy of 15,000. So you can see again at every position the total energy, if you added up the gravitational potential energy and kinetic energy, stays the same at 15,000 joules. Alright, and then here's another one, the pendulum. So go ahead and pause this video and try this one out on your own too. Alright, so if you look at the first position, position A, the pendulum has 10 joules of potential energy and is not moving, so it has 0 of kinetic energy. So you would represent that with 10 in the gravitational potential energy. And that tells us that at every position the total energy has to add up to 10 joules. So at position B, if it's 2 joules, that means that there's 8 left in kinetic. At position C, if it's at its lowest point and it has no potential energy, then it has to be all kinetic energy, or energy of motion, of 10 joules. And in the last position, they don't tell us any of the quantities, but we do see that the height at which this ball is going to, this little dotted line, is the same as it had at position A. So that means that it has the same amount of potential energy that it had at position A, which would be 10 joules, and then the kinetic would be 0. Alright, so one thing I wanted to draw your attention to is some of the different strategies that we've used in this class. We've done some things where we looked at the learning cycle of this unit, kind of an elicitation, exploring, asking questions, and then evaluating and reflecting on what we've learned. We used a strategy called stations in the matter unit, and we're also going to be doing an energy stations activity in this unit. We've had some demonstrations in class where you may have had to make a prediction. We did some investigations where you had to actually plan and carry them out, such as the consumer product testing. We did a gallery walk. We've done a couple of competitions like penny boats and roller coasters. We'll be doing an egg drop too, where you get to design some kind of product or something and test it out. And we also use a lot of different active learning strategies or formative assessment techniques, talking to your neighbors, working in cooperative groups, mini whiteboards, and also like these elicitation posters that we do at the beginning of every unit. One that we haven't really looked at yet that I want to show you is using web-based simulations to learn about physics. So there's a really neat website called PHET, or Physics Education Technologies, and I'll just go to that website and show you a couple of them. Alright, so if you get to the website, you can click on Play with Simulations, and then you can actually look at either the content area or the grade level, and we'll click on Physics. You can see there's a whole bunch of different ones. You can even focus on a particular topic area like motion. One that I wanted to show you is called Energy Skate Park Basics. Each of these tells you whether it runs in HTML, which would work on an iPad, or Java, or Flash, Adobe Flash. So this one kind of is related to what we're doing right now in terms of energy bar charts. Alright, so we'll just look at the introduction to begin with, but you can see here we have a little skater that we can put on this track, and I'm also going to click on bar graph so we can kind of see what's going on. As we put him up here, you can see that he has a bunch of potential energy, and that's also the same as the total amount of energy. If I let him go, you can see how that potential energy gets transferred into kinetic when he gets down to the bottom of this track, but the total amount of energy stays the same. So if you could add up the kinetic and the potential at any time, it would always add up to that total. Now if you want to click on this one to add friction, you'll see that over time some of that energy that we start with will get dissipated as thermal energy. So that thermal energy bar goes up and up as the skater kind of starts to slow down due to that friction on the track. And I think eventually when he comes to a stop, you'll see that the thermal energy will be equal to this total bar here, so that all of the energy that the skater started with, that total energy has actually been dissipated in the form of heat or thermal energy. And the last piece on here is that you can actually construct your own kind of roller coaster track for that skater. So it's something kind of fun you can try on your own time. Make some kind of track and then put the skater on there and see some of the energy that it has. Alright, so that's one. Another one that's really good that you might want to check out is called the Moving Man, and that one runs in Java. So if you click on the charts link there, you can actually give this person a certain velocity and then look at how their motion changes. So maybe I'll give him a velocity of 0.5 meters per second and then push play. You can see he starts to move with a constant velocity in that positive direction of 0.5 meters per second. And so you get the graph of position versus time as a straight line. The graph of velocity versus time, it's hard to see, but it's at 0.5 meters per second, and there's no acceleration in this case. So we can reset it. If you wanted to see a graph of acceleration, you could give him a little bit of acceleration, maybe 0.5 meters per second squared there, and then push play. And you can kind of see that starting to speed up a little bit. I'll stop him before he hits the wall. But you can see that we have this upward facing curve for a constant acceleration or increasing speed motion. The velocity versus time graph is linear, and the acceleration is just at like 0.5 meters per second squared. So that's something that you can play with. You can also try some negative values in there and kind of see how that affects it. Alright. So a couple other ones that you might want to check out is one about density. There are some that are about force in motion or force in one dimension. The Energy Skate Park, they have the option for an HTML version or the Java version. And also below each one you'll want to take a look. They sometimes have teacher resources or worksheets that you can use to go along with those different simulations. Alright, so this is the one that we just looked at, and then also the Moving Man. So I recommend that you take a look at some of those, especially for the motion unit. Maybe it'll help you with interpreting some of the motion graphs that we've looked at in this unit.